Welcome to the deep dive. Today we're tackling maybe one of the biggest questions out there. What if reality isn't made of dots, but strings?
Little wiggling lines of energy.
Exactly. We're diving into string theory. It's a huge idea in physics, possibly the most ambitious attempt to explain everything.
That's the goal, isn't it? Our mission today is to really unpack the core ideas from the sources you sent over, give you the key takeaways, help you grasp what it's all about. It's this potential path to a theory of everything.
Okay, let's unpack it then. The fundamental idea is, it's pretty wild. Everything, particles, forces, everything.
Right.
It's made of incredibly tiny vibrating strings.
Not point particles like we usually think.
No, not points. And when we say tiny, it's almost impossible to picture. We're talking Planck length tiny, like 10 to the minus 35 meters.
Yeah, unimaginably small. The scale where quantum gravity has to be a thing.
And the different ways these strings vibrate. That's the key, right?
Exactly. Think of a guitar string. Different vibrations give you different notes.
Mm-hmm.
Well, here, different string vibrations give you different particles.
Mm-hmm.
So one vibration pattern looks like an electron to us.
Okay.
Another looks like a photon or a quark. Even potentially the graviton, the particle carrying gravity.
So it unifies matter and forces right from the start, just based on vibration.
Precisely. It provides this sort of unified framework. It's not just a collection of different bits. They all come from the same underlying thing. The math naturally suggests this structure, fitting the known particles.
Okay, now here's where, for me at least, it gets really mind-bending. The math doesn't just work in our normal dimensions.
Right. This is probably the most famous or infamous part of the theory.
It needs more dimensions, like extra space dimensions.
Yeah. To be mathematically consistent, most versions of the theory need 10 or sometimes 11 total dimensions. So our familiar 3 space dimensions, 1 time dimension, plus 6 or 7 more.
Wow. Okay, but where are they? I'm not seeing 6 extra dimensions around me.
No, you wouldn't. The idea is they're compactified. Curled up, imagine a garden hose. From far away, it looks like a one-dimensional line, right? But get up close, and you see it has a second dimension, the circular part wrapped around it. These extra dimensions are thought to be curled up incredibly tightly, way too small for us to perceive directly or even detect with current experiments.
So they're hidden, but they're not just like a mathematical trick. They do something.
Oh, absolutely. Connecting this to the bigger picture, the geometry of these hidden dimensions, how they're curled up, could actually determine the fundamental constants of nature.
Like the strength of forces.
Exactly. Why gravity is so much weaker than, say, electromagnetism. The specific shape of these compactified dimensions could explain these kinds of mysteries that are hard to tackle in just 4 dimensions.
Which brings us to maybe the biggest appeal of string theory, unifying the forces. Gravity, electromagnetism, the strong and weak nuclear forces, getting them all under one roof. That's the dream, isn't it?
It really is the holy grail of fundamental physics, yes.
Oh.
And string theory is arguably the best candidate we have.
How?
Well, it's the only framework we know of that seems to naturally incorporate quantum gravity. It doesn't just allow for it, it requires it in a way. It merges Einstein's general relativity, our theory of gravity, with quantum mechanics.
Which is notoriously difficult.
Extremely difficult. Other attempts usually run into mathematical contradictions, infinities popping up everywhere. String theory seems to handle that junction much more smoothly.
And part of that smoothness comes from another concept, supersymmetry. Broadest USY.
That's right. Supersymmetry is woven into most string theories. It basically proposes that every fundamental particle we know has a heavier, undiscovered superpartner.
So like an electron has a selectron, a quark has a squark.
Sort of, yeah. Those are the names. And CYY isn't just an add-on. It actually solves some deep mathematical problems within the theory, helps cancel out unwanted infinities, and addresses issues like the hierarchy problem, why gravity is so weak.
But we haven't found any of these superpartners yet, have we? Despite looking hard at places like the LHC.
No, we haven't. That's a significant point. Physicists are definitely searching. Finding them would be, monumental evidence supporting these ideas. But their absence so far is a bit puzzling for the simplest CSY models.
Okay, despite that, let's talk about a major success. Gravity. You mentioned the graviton earlier.
Yes, this is huge. In string theory, gravity isn't something you add in awkwardly. It just emerges.
How?
One specific vibrational mode of a closed loop of string naturally has all the properties expected of the graviton, the hypothetical quantum particle that mediates gravity.
So the theory predicts gravity in a quantum form.
Exactly. It inherently provides a quantum description of gravity, which is something general relativity alone can't do, and quantum field theory struggles massively with. That it falls out naturally is perhaps string theory's most compelling feature.
Okay, so we've got this elegant, unified picture, extra dimensions, gravity included. What's the catch? Why isn't it universally accepted as the theory?
Well, the biggest hurdle, and it's a major one, is experimental verification.
Right, it hasn't really made predictions we can test.
Not directly, not yet. The energy scales required to see the strings themselves, or the extra dimensions, are likely far beyond what our current particle accelerators can reach.
So it's hard to prove right or wrong.
That's the criticism. Some argue it's drifted into being more philosophy than science because it's hard to falsify, in the traditional scientific sense.
But people are still working on it.
Oh, absolutely.
Yeah.
Researchers are looking for indirect evidence, perhaps through cosmology, like signatures in the cosmic microwave background, or in the behavior of black holes, or maybe subtle effects in high-energy particle collisions. It still drives a lot of theoretical research and generates new mathematical tools.
So wrapping up, we've journeyed into the idea of a universe built from vibrating strings, possibly playing out in more dimensions than we see, unifying all of nature's forces. It's a profound shift in perspective.
It really is. And it leaves you with this thought to consider. If the universe truly is a symphony of these strings, constantly vibrating, what happens if we learn to read the music?
You mean understand the melodies and harmonies?
Yeah. Could understanding them fully unlock not just secrets about the universe's past and future, but maybe even give us new ways to interact with the fabric of reality itself? What new tunes might we discover or even learn to play?